Let's have a look at a utility function in MATLAB. The purpose here is not to teach you MATLAB, but simply to illustrate what the graph of a utility function looks like. I begin with plots, which allow me to draw three-dimensional pictures. I define a utility function. U : equal to is how to define a function. You do x1, x2 in parentheses to tell Maple that those are your variables that the function will depend on. Then you do this arrow to the right, which you construct by typing a minus sign and a greater than sign. Then finally you type the actual function. In my example, my utility function is simply 4 times the amount that I consume of good 1 times the amount that I consume of good 2. You can also click on this symbol to create a function. To try it out, we can evaluate this function at 3, 3, and that will give me a utility of 36. If you want to make a 3D plot of this utility function, do plot 3D, the utility function, then you do the domain. I will let x1 vary between 0 and 3, and I will do the same thing with x2. I will use a special style, the surface contour. The surface contour option will give us these lines, which I will come back to later. So we have x1 along this axis from 0 to 3. We have x2 along this axis from 0 to 3. And we have utility along this axis. If I just turn this around like this, we can see that at the origin, when both x1 and x2 is 0, utility is 0. Utility will also be 0 along this axis because then x2 is 0. Same thing with this axis. Up here at this point, x1 is 3 and x2 is 3 and the utility is 36, which we can see here. So this is a 3D plot of this function. This utility function for x1 times x2. So getting back to these curves that you see on the 3D graph, which are drawn simply because I typed this command surface contour here. Along these lines, the value of the function is constant. Exactly what the value is, you cannot see from the graph. But if we look at it a little bit more from the top, like this, we can see that for all these combinations of x1 and x2, the product 4 times x1, x2 is the same. The value of the function is approximately 3 along this line. Over here, x1 is around 0.25 and x2 is 3. 4 times 0.25 times 3 is 3. As we move down and to the right, x1 increases, x2 decreases, keeping 4 times x1 times x2 constant. At this point, x1 and x2 are equal, a little bit below 1 each of them. And then we can move up along the curve. The level of utility remains the same. I have more than one of these curves. So I have another one right here. The same thing is true. The utility level, or if you like, the height of the curve is the same at all these points. But the utility is higher at these points compared to these points. And as you move upwards, you get a higher and higher level of utility. We can see that a little bit more clearly if we look at it from the back. All points on this curve are at the same height. If I do it like this, it becomes pretty clear that that is the case. So what we will do next is to make a 2D plot of these curves. Let's spin it around so we have x1 along the x-axis and x2 along the y-axis like this. So we will make a 2D graph by projecting these surface curves onto the x1, x2 plane. I'll turn it a little bit like this to demonstrate what we will see when we project these lines onto the x1, x2 plane. In Maple, you do that by typing contour plot. You do a parenthesis, You have your utility function, the range of x1, the range of x2. All this is the same as the 3D plot. Then there is an optional command called contours. I put the numbers 4, 8, and 11. That will instruct Maple to draw 3 curves. The first curve should be all combinations of x1 and x2 where utility is equal to 4. Same thing, second curve, but the utility should be 8. And here for the third one, utility should be 12. So here is what it looks like. This first red curve is the collection of all points x1 and x2 such that u is precisely 4. For example, this point right here, when x1 is 1 and x2 is 1, will give me a utility of 4 times 1 times 1, so that's 4. Same thing, this point must be on the graph. 2 times 0.5 times 4 is also 4, and so on. All points on this curve will give me a utility of 8. For example, right here, 1 times 2 times 4 is 8. And all points along this curve will give me a utility of 12. So have a look at these two graphs. This is the actual utility function. It's a 3-dimensional graph. This is a projection of these level curves where the level of utility is constant projected onto the Cartesian coordinate system of x1, x2 bundles. Let's just add this utility function to our PowerPoint presentation. And here are 3 level curves of this utility function. The reason I'm spending so much time on this specific utility function is that this one and minor versions of it are some of the most common utility functions in microeconomics. It's the simplest utility function which will represent well-behaved preferences. As we will see shortly, these level curves are indifference curves. As you can see, each indifference curve is strictly decreasing and convex.